Okay. Now, we have already seen that so far. Power electronics is a switching technique. That's why some people call it, it's not power electronics, it's actually power processing, they call it. Anyway, now this one we studied. Just refresh our memory. If your capacitor is empty, there is no energy stored in it, this voltage source produce huge amount of current. Thanks that we have a resistance here to limit. I'm sorry, just a moment. Oh, you can't see me, by the way. You'd better see me if you want. Okay. All right. So then, because of the resistance, the current is limited. Then, while the capacitor is charged, the current is decaying. We develop the equations of those. That is exponentially decaying, and that one is exponentially rising and reaching the limit of this voltage. You remember that. We have already studied that. And these are the equations. I use different equations. You remember that. If you have a network like this, that means your capacitor is charged and a diode is connected. So if you come back here, you just assume that you have a diode is connected here. You have a diode is connected in this direction. So if your capacitor is charged, then that kind of current is going to flow. That kind of current is going to flow. That is the one. That is the one here. You see, the capacitor is charged and the current is flowing. Current is flowing in this direction. In that case, the energy stored in your capacitance is discharged through that line. Current is, and also the voltage parallel, of course, voltage is discharged. We also derive those equations to you. Okay. Now, I also derive the equations here. Since if you put that switch on, then since your inductance hasn't got energy stored, the current is not going to build up. Never forget that. The capacitor intends to keep the voltage, parallel voltage, constant. Inductor is the one to make the current rising later. So capacitor wants the voltage constant because of the stored energy, or it is difficult to rise the voltage of the capacitor, parallel capacitor. Similarly, it is difficult to rise the current in your inductance. That is the current. It takes time. Why it takes time? Since you are actually storing energy in your inductance. Finally, the stored energy here is equal to energy here ben bıktım bu kalemden ya. Vallahi billahi ya. Parmağım değdiği anda başlıyor daha değdirmeden yazmaya. Ama onsuz da hiç yazamıyorum. Özel bir kalem. Merak ediyorsanız burada. Bu da bu. Gördünüz mü? Evet. Böyle bir şey. Belki kamerayı koymak zorunda kalacağım biraz sonra. Dur bakalım. 1/2 L IS square. The energy here is this. So you are actually, while current is rising, you are actually storing energy in it. And at the end, you reach the steady state. We have already derived those equations, and we have seen that voltage of the inductance, if there is no current, all the voltage measured here, all the voltage measured here is equal to supply, of course. Then while the current start flowing, then the voltage drop of the resistance is the difference between that voltage. So but the current is rising exponentially. I derived those equations. I'm not going to do it. Then, of course, the voltage between the terminal of the inductance is getting down. Similar to the capacitor current. Whatever happens in capacitor is opposite in inductance. Inductance delays the rise of the current. Capacitance delays the rise of the voltage since they are storing energy. The stored energy in capacitance is 1 over 2 CV square. In Turkish we call it 1 bölü 2 CV kare. Yes, this is what we have done last week. And these are the equations. Although I derived those equations in different manner, but the result is the same. Now, what about that circuit? That circuit is LC circuit. Okay, so carefully look at it. So then I'm going to derive those equations in an empty page. Okay, so we have a source DC, we have an inductance and capacitance. Be careful, there is no resistance. Now I'm going to open a new page for you. Main objective is to learn the basics of the topics. Not, of course, detail is important, but you learn the basics. Of course, our lab purpose this afternoon, I know you have a lab session. Main purpose is going to be learning the fundamental of it. Now, let's have a look at that circuit. We have a voltage source. We have a switch. We have a diode. And we have an inductance and capacitance. L, C, diode. And voltage source. Voltage source is DC. We supply plus and minus DC. Okay. Now what's going on here? We are going to write the Kirchhoff voltage law equation. Vs is equal to L di dt plus Ri. I'm sorry, I made a mistake. I made a mistake. I've been thinking something else. L di dt plus 1 over C L di dt L di dt plus 1 over C integral I dt. Now, we'd better use S domain. This is a step function. So Vs over S is equal Ls plus 1 over Cs Is. Is is equal to Vs over S Ls plus 1 over Cs, which is equal to Vs over L çok uzatmayacağım. Hemen L parantezini alayım. Vs over L bracket 1 over S square plus S square plus 1 over LC. Bu da eşittir. Vs over L one over S square plus omega O square. So that means, so the inverse Laplace of this one is a sinusoidal function, and which is equal to Is it is equal to Vs times C over L sine omega ot. So omega is here, omega O is our resonant frequency. So that means what you are doing actually, there is no loss. So whatever the energy you store in your inductance and whatever the energy you store in the capacitance are transferred to each other. You understand that one? So this is a resonant network. It's ideal network. Of course, every inductance has got a resistance. Every capacitor has got a resistor because of their inherent structure. But if you neglect those resistors, that equation is valid. Omega O is equal to it's a well-known resonant network. So DC network actually produce AC. And the waveform is going to be something like this. the current, this is a sinusoidal waveform, so it's going to start the sinusoidal waveform. So the current is going to be something like this. Time equal t1, what's going to happen? Time equal t1. What's going to happen? Remember, there is a diode here. Diode is not going to allow you to current drove to the negative value. So all of a sudden, at whatever the particular point would be, your switch is going to turn off. Okay, so this is the moment. This is the moment current becomes zero, and then no current will flow. Whatever the energy stored is remains. And the voltage of the capacitor here, by the way, Vc T is equal to, you remember that 1 over C integral I dt. Therefore, Vc T is equal to Vs 1 minus cosine omega t. I think you can read that one. Omega, bunu biraz da düzelteceğim çocuklar. Şimdi siz bu sayfaları çünkü hafızaya alıyor bilgisayar. O yüzden burada yazıyorum. Sanki tahtaya yazıyorum ve siz resmini çekiyorsunuz gibi. Technology is giving us some opportunities. We have to use those. So Vs 1 minus cosine omega O t. Tamam. So that means is this. If it is all right so far, we have already obtained the current function, which is a sinusoidal, the red one. This is the current. I. Şu nokta önemli mi sizce? Şu nokta önemli. Çünkü şeyin yani pi bölü 2'ye karşılık geliyor. It's equal to pi over 2 or equivalent to pi over 2. Therefore, it's a peak value. V maximum. Bu değerde burada yerine koyarsanız, if you put that one here, you are going to see that I'm going to come back to original waveform. I come back to the original waveform. Pardon çocuklar. Bir yanlış hareket yaptım. Manevra yanlış yaptım. Onun için dosya geri gitti. Şimdi açtım. Tekrar. I open it up again. I lost some time. So, we have already derived that this waveform is the current here, and that waveform is the capacitor voltage. So the capacitor voltage is negative at the beginning. Bir dakika ya, bu devre değil ki bizim devremiz. This is not our equivalent. That is the one. That's the one. That is the peak. That is the peak. And that is the capacitor voltage. So capacitor voltage at T equal T1, which is equal pi times square root LC, is equal to 2 times of the supply voltage. So this is a typical network, resonant network. If you do allow that network, then it's going to oscillate. If you provide a negative diode here, for example, if you provide a negative diode here, hypothetical of course, negative diode here, so it's negative diode here, so it's going to, the energy is going to be flowing as a sinusoidal here. It's going to be continuing in negative direction as well. So from DC you provide AC, okay? Anyway, but that is not our case. Our case is this. We haven't got any negative diode or something like this here. We have a single direction device here, and the current is going to sinusoidal. It's a resonant network, and the voltage is going to be double of this one. These are the equations I have already derived for you in S domain. That is the voltage of the capacitor. So if you put that value is equal T1, then it's going to be minus 1. Minus 1 multiplied with minus is 1. 1 on 1 is going to be equal to. That's why we say the voltage of the capacitor becomes twice the source voltage. This is also another example. If your capacitor is charged, fully charged, then what's going to happen when you put this switch on? Of course, you have a negative diode. Then the capacitor voltage, which is starting from, let's say, from negative or starting from positive, doesn't matter. So it depends which direction you are taking this one. But that is your reference. Don't forget that. And then the current is going to be again a sinusoidal, and then the voltage is going to be changing from minus to plus or plus to minus. Okay, I omit that one. I'm not derived the equations. Now we have another problem, RLC network. You remember from control theory, if we have a network like this, however, this one has got a DC source. What kind of structure do we expect from this? biraz bir iki denklemi buraya yazayım çocuklar. That one here actually is an IGBT. Sorry, cursor. This one here is most likely is IGBT. So you can turn it on if you want, put it on, and put it off if you want. So you define it's a fully controlled or MOSFET. You might use a MOSFET as well. Now the equation is going to be sorry about that. Ri plus L di dt plus 1 over C integral I dt equals 0. Assume that stored energy in inductance 0, stored energy in capacitance 0. That means there is no current initially, current is 0, and there is no voltage here charged. What are you going to do? We are going to write the Laplace form of those. Şuraya yazayım onu ya çocuklar. R plus LC plus 1 over CS. Alışkınsınız buna, ben biliyorum. IS is equal to Vs over S. Vs is a step function. So Is actually is equal L S square plus Rs plus 1 over C. Şu 1 over C'den hiç mutlu olmadım. Bir dakika. One over C. Oldu. Sığdı. Şimdi tabii bu sayfa böyle bitti. Ben artık şekli bozmayayım. Bunun üstüne devam edeceğim çocuklar. I'm going to continue on this one. So if you are happy about this one, you just write the Kirchhoff. So the current is going to flow. Current'ı da gösterelim. Hala şeyde ya o. Çizime geçelim. Current is going to flow through loop. So that is the one which is going to flow, and in S domain that's the version of the current. So I continue. I clean up this page. And I continue on current version, current equation rather. Is equal to Vs over L S square plus R over L S plus 1 over LC. Şimdi şuna delta diyelim. Delta S12, you are familiar with that one from control, minus B over 2A plus M minus B square minus 4AC, a well-known divided by 2A, a well-known equation. So from that one, S12 is equal to minus R is equal to minus R over L, minus R over 2L plus M minus R over 2L square minus 1 over LC. Mutlu değilim buradan. Bunu bir daha yazacağım çocuklar. Sorry. Güzel olmadı. Yer var nasıl olsa. We have room here. Muhammed Sadık, I expect you to come at 9 o'clock. Probably you were there and drop. I don't know. Yeah, that's right. So that is the equation. The roots of this one. And so result S12 is equal to minus alpha. Efendim Muhammed.
Yes, Professor, how did the 4AC become 1 over LC?
Sorry, can you repeat, please?
I was saying, how did the b square minus 4ac under the root became r over 2l squared minus 1 over lc?
I check it up twice. You write down, you are going to find this one. Okay? So,
Okay, thank you.
Mohammed, it's not very difficult. You are just going to use that. You are just going to use this equation. Okay? So you are going to put b here is r over l. Okay? So r over l square, r square over l square. Okay? Divided by 2 times, so 2 times divided by 2, so since it's here, so that means it's going to be 4. Don't forget that. This when you put it inside the square root, that 2 is going to be 4. Okay? You can do that. All right. Thank you. Thank you for
Thank
following
you.
the material. So it's going to be minus alpha plus and minus it's a second order system. You are familiar with those equations from our control systems. Not in this form, but similar. Alpha square minus omega o square. Alpha here, onu da kırmızı ile yazayım görünsün. Alpha is equal to r over 2l and omega o is equal to 1 over square root LC. Okay, so that is the equation. Who is going to interpret that equation? There are cases. For example, if alpha is equal to omega o, so square root part is become 0, and the S1 and S2 are equal. If S1 and S2 are equal, so what's happening? It is critically damped case. You see, that is very important. Learning something from one course is not only belong to that course. Learning something, this is actually a circuit theory. So you are learning from circuit theory, we implement it in control, now we are using the same theory into the power electronics. So if, I repeat, follow my cursor, if alpha is equal omega o, that means this part becomes 0, and then S1 and S2 are equal, only a one value is, of course, it's minus, so it's stable, but you have only the two roots are equal, so it's critically damped case. If, however, alpha is higher than omega o, that means you have also a real term here and another real term here. So you have two roots. It's overdamped case, but two real roots, overdamped case. If your alpha is smaller than omega o, so that means this negative part, the inside the square root, there is a signature becomes negative. Therefore, a J term, imaginary pole, is going to be obtained. If you have an imaginary pole, it is underdamped case. Okay, I'm sure you understand that. So I start from very beginning. I just derive. Follow me, please. Follow my cursor, please. Hatta siliyorum artık. I just derived the equations for RLC network. I have obtained the time domain solution, or sorry, I'm in the still S domain. I obtained the S domain solution, and I have realized that current might be under certain circumstances. Alpha is equal to S12 S12 current denklemindeki S12 is equal to minus alpha plus and minus alpha square minus 1 over LC. I'm sorry, omega O. Bir dakika. Don't do what I do. If I think something else, I just write automatically a wrong equation or wrong term. Omega O square. So alpha is equal to R over 12, and omega O, which is a resonant frequency, angular frequency rather, 1 over square root 2 LC. So we are now evaluating the current roots. Current equation roots are saying that we might have critically damped case, we might have overdamped case, we might have also underdamped case as well. Now I continue equation. What Mohammed is writing here, that is the equation I have already written, that equation. And that one is the roots of the, I have already shown that one to you, derived rather. And that's the resonant frequency omega O and alpha already given, okay? Then case one, if alpha is equal to omega O, then the roots are equal, S1 is equal to S2, and the circuit is called critically damped. And solution is going to be something like this. What kind of function is this, by the way? True, this is exponentially decaying term, but that one is also proportional with time. But slope is exponentially decaying. Sorry, I'm sorry, it's not decaying. It's a plus. Depends S1. S1 is a minus value anyway. It's a decaying. Azalan, exponentially reducing waveform. S is a negative. You remember that. S here is a negative. So that these two equal each other. So S is a negative. Therefore, it's a exponentially reducing waveform. Case 2, the roots, both root alpha higher than omega O, the roots are real, and the circuit is to be overdamped. I emphasize that. The solution takes this form. And case 3, if alpha smaller than omega O, the roots are complex. Of course, there are real and imaginary parts, and system is called underdamped. The solution is that case is something like this. That is resonant frequency, and that is the exponential term. So the waveform of this one, you are familiar with that waveform from control theory. This is actually a sinusoidal waveform, kind of sinusoidal with delay, anyway. But envelope is exponential. So the current waveform is going to be something like this. This is the current waveform. Şimdi çocuklar, bir problem var kitapta. There is a problem in your book, and that problem is such that we have an RLC network. C value is given, voltage is given, L is given, and resistance is given, and the capacitor is empty, and there is no current in inductance. There is no stored energy in neither capacitor nor in the inductance. And at time equal 0, if you turn on the switch, what's going to happen? Hadi bunu ben TED'de hızlı yazacağım yalnız ha. Çocuklar, kamerayı getirecektim fakat kamera biliyorsunuz şey yapmıyor. E, hatırında tutmuyor şeyi. Yürüyorum. Evet, biraz uzun olacak benim için ama bakalım. Şimdi bir kere şuraya şeyimizi ayarlayalım. 5 punto çok kalın. Biraz ince yazalım ki küçük küçük yazabilelim. 2 puntoya getirdim. Şimdi R Vs is 220 volt DC. L is equal to millihenry. R is equal to 160 ohm. C is equal to 0.05 microfarad. That's all. And there is no stored energy. When you turn the switch on, alpha is equal R over 2L. Radian per second. Omega O is equal 1 over square root 2 LC equal times 0.05 times 10 to minus 6 equal 10 to power 5 radian per second. So angular frequency omega O is 10 to 5. Damped resonant frequency or ringing frequency, damped resonant which is ringing frequency eşittir omega R. Omega R is equal to omega O square minus alpha square. You remember that one. For omega R, which is equal to bu 10 üzeri 5'ti. 10 to power 10 minus 16 times nerede o? Alfa kaçtı? Alfa 40'tı. 4 kere 4 16'dır. 4 times 4 is equal 16. 40 times 16 times 10 to 8 which is equal to 9, 1, 6, 5, 2 radian per second. Aslında 1 bölü second yazsanız da doğru ha. Since radian hasn't got any unit. Solution was, şimdi onu kırmızı ile yazayım da birazcık değişiklik olsun, dikkatinizi çeksin. Solution was IT was e to minus alpha t a1 cosinus omega rt plus a2 sine omega rt. You remember we derived that equation. So initial value time equals 0, current is equal to 0, A1 is equal to 0, and the equation here, IT becomes alpha t times, paranteze lüzum yokmuş, di dt is equal to Vs over L. I put a note here. It's a circuit theory, I said. Time equals 0. Time equals 0. At time equals 0, yes, I know that. For time equals 0. At time equals 0, yes, I know that. For circuit theory, time equals 0, the di dt is equal to 0. Sorry, di dt is equal to Vs over L. Bir dakika. Moment. Di dt at time equals 0 is equal Vs over L. Which is equal to omega r times A2. So A2 is equal to Vs over omega r times L. Şimdi buradan devam edecek olursak next page'e, you understand that one. We already applied that simple equation actually. So for cursor, yeah, that's right. We use that equation, and we also derived those equations. We already given those values, so we calculated the values here, and then we are going to obtain A1 is equal to 0, A2 is equal to this. Now I'm going to employ that one in the red equation for the next page. A2 A2 is equal to that is the equation we obtain, and the conduction bir de şeyi sormuş. Conduction time of diode Conduction time of diode is omega R times T1 is equal to pi. Therefore, T1 pi over microsecond. Bir bakacağım şeyinize. Problemi bir daha bir okuyayım çocuklar. I'm going to read the problem. The second order RLC network in figure has the source voltage is equal VDC 220 volt, inductance is 2 millihenry, capacitance is 0.05 microfarad, and resistance is 160 ohm. Initial value of capacitor voltage is equal 0, and the conductor current is equal 0. If switch S1 is closed at time equal 0, determine an expression for the expression for the current IT, and B, conduction time of the diode. Draw a sketch IT. Current'ı da çizin diyor. Draw the current. So this one is the conduction time of the diode. Şimdi geri dönüyorum çocuklar. I come back. Burası herhalde çözdük problemi. Artık bir sorun yok. Tekrar geri dönüyorum. Evet, devre bu. That's the circuit we have, and we solve the problem. These are the equations already we have seen. The cases, we have 3 cases. This is a final one. This problem is special designed for this case. So it's and the solution of the problem is this. That is the 1.2 e to power minus 4000 t is the exponential term. So this is the envelope, and that is the current waveform. So you can see that the current is going to become 0 at pi. This system is not allowing a negative current again. That is one important conclusion. That's why probably Mohammed Rashid put that problem in it. It's a sinusoidal current, but be careful. The current cannot continue in a negative path because of the diode. Okay. Otherwise, eğer öyle olsaydı, if would have been like this, it's going to be something like this. Bakın. Eğer bir ters diyot falan olsaydı, kırmızıyla devam edeyim. It would have been böyle devam edecekti. Ama etmiyor. Tamam mı? Yani şöyle Siyahla ben onun üstünü, siyah olmaz. Öbür resimle karışır. Mavi ile onun üstünü bir çarpılayım. Öyle bir şey yok. Tamam mı? There is no such thing. Now what's going to happen that kind of network? Oh, this is a SPICE solution, by the way. This is a SPICE solution. Changing the parameter. You can change the parameters. The resistance of the network, you can change it. That is the waveform. We have already derived those equations. I'm just going to give you brief information. We have already done it. When you put it on, current is going to flow through that line. I'm sorry. Current is going to flow through that line. And then energy is going to be stored here exponentially. That is the current waveform. Current is going to flow like this. Probably it's going to reach steady state. When you put this switch off, then because of the stored energy, current is going to flow, continue to flow in this direction. Onu da başka renkle göstereyim. That is the current. I derived those equations for you. I remember that. The red one. That is the diode current, this one. Okay. You already know those equations. Mode 1, when current is rising, I derived those equations for you. For this is a LR network. And when you put it off, you obtain the initial current, and then in freewheeling mode, this is the equation, and the current waveform is this. I derived those equations for you. What about that one? Who is going to explain it to me? This is the last topic. Çabucak anlatayım, yorgunsunuz. Biraz ara vereceğim. O aradan evvel anlatayım bunu ama. I'm going to explain it to you. VL is equal to LDI dt. There is only inductance. So DC source is connected to inductance. Okay? And current is going to flow through that line. Since V is equal, since V is equal LDI dt, then bu ters çıkmış ha. Çok enteresan. Niye öyle çıkmış? Allah Allah. Ben bunu başka bir yerden kesip yapıştırdım ama ters yapıştırmış kendisi. Neyse, netice itibariyle this current is equal to that one Vs over L dt. Yani bu dt'yi tutun burada, dt'yi bu tarafa alın. paydadan. Vs 50'de 1 bölü L yapın. Şu enteresan. Bunu karalayalım böyle. Hiç görünmüyor yani. Çünkü ne olduğu belli değil. So current equation is the integral of this one. What kind of integral is this? I yazıyorum. Bakın buraya benim yazdıklarıma bakın. Since Vs over L dt is equal di. So I is equal to Vs over L integral tabii. Integral dt. O da bu. O da eşittir Vs over L t'dir aslında. Tamam mı? Doğru denklemidir. It's a line. But at t equal t1 we turn it off. Then who is going to explain the next? Since there's no resistance, you already store energy in your inductance. Current is going to continuously flow infinitely in theory. So that is the current. Temizliyorum burayı. So at this point, current rise like this, without turn it off, current goes up, by the way. Current, without turning it off, current is going to increase like this, without turn off. Of course, burn down the transformer. If it is a transformer, for example, that DC, that's why people call it, don't give a DC current to a transformer. That is the reason. DC current rise and put the transformer or core in the saturation and excessive current flows. But in power electronics, we switch it off. Evet çocuklar, benim saatim şu anda 10:16. Size 10:30'ye kadar vakit veriyorum. Şimdi 10:30'de ne olacağını gördünüz mü bilmiyorum. Şeyi açın. I'm sorry. I give you a break to 10:30. At 10:30 there's a quiz. Bir temiz sayfa açayım. So 20 minutes only. Okay? So you are going to send it to my, so you know how to do that. Online exam. Tamam mı? So take a break and I expect you to start quiz. Thank you for listening so far. At 11 o'clock, or probably, yes, 11 o'clock we are going to start, okay? Another course. You have only 20 minutes, by the way. Don't forget that. Good luck all. Right, Nasrullah. Right, Hasunah. Your exam paper is not opened. Try to send it again. There is something wrong with that one. Time is over. Time is over. I told you until 10:50. Yeah, well, yes, yes, right. I can't do anything about it. What happened that? Ali Umut Terzi bilmiyorum ne yapacağım. Yani bunları yani test yapmadığım için okuması gene nereden baksan adam başı 10 dakika ayırsam yani işte yani bir 3-4 saatlik bir mesai istiyor. Bilmiyorum. Right. You send me an email to my box to my email address. I don't know why you can't it. You can't send it. You send it, but it's not opened. Probably there is something wrong with your system. Okay, in 5 minutes I'm going to come back. Evet. Now we are starting again. Now we are starting chapter 3, diode rectifiers. For this chapter, you are going to learn the performance of a DC and AC network to be used by diodes. Okay, one of them. These are the terms. Of course, it's already over there, and sorry. That is, for example, an AC to DC conversion. We have to start from this point. I'm just going to give you one example, one rectifier, for example. This is a AC to DC conversion. So the input input V voltage time is equal V max sine omega t. Sinusoidal function, input. So input is something like this. This is time. So input is something like this. Vm is the peak value, Vm, maximum value, and this is Vt. Just assume that we have got a DC from this, such that, for example, we convert this part and get that waveform. We convert this part and get that waveform. Output. Assume that output is something like this. Şu şeyi siliyorum aşağıdakini. Negatife izin vermiyor. We are not allowing negative portion. And output is something like this. What's that one? Input is AC sinusoidal, but output is if you have an average value, V average is VDC. Çiziyorum kırmızı şeyle. Şu mesela bunun V average'i. V average is equal to 1 over t from 0 to t function t dt. We have already discussed that one. So if I come back to original part, so this one might be your output or siliyorum artık. Input is sinusoidal, by the way. Your output might be like this. There is an average value. Ideal DC, it says, Mohammed writes here, ideal DC means that it is actually, Mohammed Rashid, it's actually an average value. You start from AC, you get a DC. Now, you have DC components and AC components. Now I continue. For output, DC is equal VDC times IDC. Power is equal to VDC times IDC. But output also an AC power as well, since output has also an undulation waveform. It's not a constant flat. Be careful. It's not a constant flat. It is also has AC components in it. Then PAC is VRMS times IRMS. Okay. So one thing we have learned, although the average value, as long as average value is not equal to 0, that is DC. But the actual average value is a DC component here, that one here, and current and VDC. However, AC components also available there. So if you continue the equation here, the efficiency, we are still in the DC side. For DC, output DC, but it has AC power in it also. AC component, let's say. That is VRMS times RMS. Bunu atın cebe, unutmayın. Now, what is the efficiency or rectification ratio of a rectifier? Which is a figure of advantage, merit, how quality, or how effective your rectification. A DC component over AC component is efficiency. So AC component here is equal VRMS square. Bunu ben biraz başka türlü yazmak istiyorum çocuklar. Yazacağım. I'm going to write it in different form. VAC square is equal VRMS square times VDC square. So it has, you can see that it has the AC component also, the effective value AC component of the output voltage could be calculated by using that equation. Or you might say that DC component You might write it in this form as well. Tamam mı? VDC component is equal to, bir dakika yanlış yazdım. Siliyorum. Eksi işaret var orada. Ters yazdım. Gördüğünüz gibi çocuklar, en ufak bir dalgınlığa fırsat vermemek lazım. Türkiye çok heyecanlı günlerden geçiyor. Yani kafam habire başka şeylere gidiyor. Takdir edersiniz ki yani bu deprem çok büyük bir üzüntü yarattı. Bir de üstelik şimdi işte seçim vesaire konuları konuşuluyor. Yani memleketimin geleceğinden ümitliyim çocuklar. Ben e, kaç senesiydi? 78 senesinde doktoramı bitirdim İngiltere'de. 5 yıl kalmıştım. Yani orada yerleşebilirdim, kalabilirdim. Yahut da yani Avustralya'da, Kanada'da, Amerika'da işler vardı. İş teklifleri vardı. Yani hiçbirini düşünmedim. Koşarak geldim buraya. İnanın acayip mutluyum. Yani memleketimde olmak, memleketimde işte epeyce bir katkım da oldu diye düşünüyorum. Memleketimin insanına bir şeyler katmak. Bu yani küçük de olsa bir şey katmaya çalışın sizde. I'm sorry for Turkish. I've been talking about the value you are going to get to your people. This is very important. And and also I'm now trying to concentrate power electronics, which is very important for us. Power electronics is a heart of electrical engineering. Don't forget that. It it is heart, kalbi. Okay? So yazayım şunu. VDC component square is equal to VRMS component sıktım ama VRMS square efendim dinliyorum. El kaldıran. Okay. Okay, Mazen. Don't worry. It's all right. As long as you concentrate on the course, I'm happy. RMS square minus VAC square. Allah Allah. Tamam. Tuhaf sayfalar açılıyor böyle Twitter şeyden bana habire portaldan haber. Anyway, so bu önemli bakın. Bu son şu kısım önemli. That part is important. That part. This part is important. Kürsörü çevireyim ha. DC is equal to RMS minus AC. So RMS means that RMS including also AC component as well. Okay. So RMS is not only DC but also it has the AC component as well. Buradan zaten anlaşılıyor. Bir dakika ya. Bir dakika. Burada da yanlış var. Burada da yanlış var. Hay Allah. Bir türlü toparlayamıyorum kafamı çocuklar. Yani bu ara verdik ya, bana iyi olmadı. Siz imtihandayken ben televizyon izledim. Bu iyi olmadı benim için. Anladınız ne demek istediğim. Siz de uyarmadınız ama ben buraya pat diye yanlışı yapmışım. Şu denklem daha önemli bir denklem çocuklar, bakın. Şunu tutun aklınızda, şunu. Yani mantığa hitap eden bu. Eğer RMS'in içinden, RMS her ikisi de var demektir. RMS'in içinden, I'm sorry for Turkish, if you take the AC component out of RMS, then you obtain the DC component. But the calculation is relevant to squares, not the directly itself, because of the mathematics involved with RMS. Now for the DC part, RMS value over DC value is called form factor. The form factor here. And the AC over DC is a ripple factor. Ripple factor. Form factor and ripple factor. Ripple factor is AC over DC. Şimdi şöyle bir dalga şekli çizeceğim. You are going to understand better. We have a waveform like this. Okay, this is time. This is a function. V output. Output T. Time function. This one means that the DC VDC plus VAC. This one is AC component, is a DC component, and this the relationship between those is already known. Now form factor is the RMS value over DC. RMS means that you are including DC and AC together, okay? But ripple factor is very clear. AC, that AC component divided by DC component. This reflects the ripple value. Tamam mı? Şimdi definition'larımızı yaptık. And also ripple factor is equal to form factor minus 1. You can derive those equations easily. There is another component which is called transfer utilization factor, DC over VSIS, okay? Now, I just start from very beginning. We have AC input, follow my cursor. We have an AC input, we have an output which has got that kind of waveform. That kind of waveform means that you have pure DC and you have an AC like this. Okay, so this one is a AC component. That one is AC component, and the pure DC, this one. That one is a pure DC. However, if you take that waveform, the black waveform, if you take that black waveform, this you are going to start with RMS value. So DC is equal VDC IDC, pure DC. AC means RMS times the AC power. Ben olsaydım power derdim buna. AC dediği zaman kafa karıştırıyor. Sadece AC komponentinin power değil. RMS. Current RMS and voltage RMS. However, the relationship between RMS minus AC component is giving you DC. Or otherwise, the RMS minus DC de AC'yi veriyor. Tamam, mutluyuz herhalde burada. Bir daha kontrol ettim. Form factor RMS'in DC oranı. Form factor is RMS over DC. Ripple factor AC to DC. And the relationship between form factor and ripple factor is that ripple factor is equal square root of the form factor square minus 1. There is another one. Generally, in front of the rectifiers, we use transformers. So transformer utilization factor is the output pure DC over input. Now we are involving input. In input, we have current called IC. Burada blue kullanmamışım. Blue'yu kullanayım. Blue color I'm going to use. We have input current IC as well. Of course, you have supply voltage, which is AC, time function. Even sinusoidal, VST, T is equal Vm sine omega t. Okay, so continue now. There is an AC side as well. For AC side, transformer utilization factor, DC component over apparent power, input apparent power. These are RMS values, by the way. VS, NIS, RMS values. Don't forget. So this is a typical apparent power. And if you continue in that power factor, however, AC power over VS over IS. Input power input power over input apparent power. Power factor çok önemli bir şeydir. Power factor in power. Crash factor, however, input current peak over input current RMS value. Bunu anlatacağım sonra. Crash value nerede kullanılır gösteriyor. I'm going to explain it to you. Now let's look at this one. It's easy now. Hemen buraya hızı vereyim. Eğer şu gerilime VS dersen, şu gerilime, bunu yaptım size daha evvel. Bir daha yapacağım artık hatırlamanız için. If you call it VS is equal VM sin omega t ise, now this positive part is transferred by diode 1. The negative part, which voltage is already negative, therefore is positively biased, is transferred to the load with diode 2. So the average value VDC is equal to 1 over pi integral from 0 to pi Vm sin omega t d omega t. Therefore, VDC is equal to Vm over pi minus cosine omega t from pi to 0, which is equal to Vm over pi minus cosine pi plus cosine 0, which is equal to V average is equal VDC, in other words, 2 over pi Vm. Maximum value'nun 2 katının pi'ye bölünmesi, divided by 2. This is the value we obtain. That's the average value. These figures here are representing the diode voltages. Each diode receives the maximum voltage in negative direction. So while you are selecting diodes, you have to consider that negative voltage as well. Okay? Let's continue. Oh yes, it's already developed. Bakın, instead of mine, he puts 2 here. 2 over t from 0 to t over 2, and it solves like this. It's the same result he obtains. You can see that 2 over pi Vm. I hate that kind of representation. I always use that equation. I always use that kind of representation. There is a logic behind this. You are going to understand for three-phase network that this logic also continues like this. Anyway, so if you have a bridge network, what kind of operate? You have a transformer as well. This is the primary side of the transformer, and this is the secondary side of the transformer. So that current here kalem gene yapacağını yaptı. Eşek. I primary, I secondary. These are the reference directions of this one. So now we have to consider the system in detail. This is the supply voltage. Follow my cursor, please. This is supply voltage. And when supply voltage is between 0 and pi, that means for the first 10 milliseconds, since frequency is 50 in Turkey, total period is 20 milliseconds, and the half of it is 10 milliseconds. So between 10 milliseconds, the diode D1 gets a positive biased voltage. Anode cathode voltage is positive. And in the meantime, diode D2 is connected to the negative part of the voltage. Then this one also receives negative, cathode receives a negative voltage. That means anode cathode voltage is also positive. D1 and D2 are conducting. So for this part, D1 and D2 are conducting. Then current is going to flow like this. Through the load and complete this network. Therefore, the terminal voltage follows this pattern. However, between pi and 2 pi, supply voltage becomes negative. That means D3 is receiving positive anode cathode voltage and D4 is receiving positive anode cathode voltage. Since the potential of the cathode of D2 is negative, that means anode cathode voltage is positive. And also if you look at D4 now is connected to this point, since the D4 is receiving D3 is receiving positive anode cathode voltage. D4 is also receiving a positive anode cathode voltage. Since the cathode is connected to the negative point, so that receives a positive one. So for this part, current is going to flow and transfer the negative portion to the positive part. Kırmızıyı bir daha ayrı çizeceğim çocuklar. Current is going to flow Tam anlaşıldı mı? If you understand properly, then D3 and D4 are conducting between those periods. If it is understand properly, we can calculate the average voltage. Onu başka bir renkle yapayım. Kırmızıyla maviyle karışmasın. I'm going to change the color. Evet, benim kullandığım renklerden biri çok görünür şudur. VDC is equal to R over pi Niye böyle yazdım? If I calculate the average value for the first half, same is going to be repeating the negative half as well. This is VDC, DC value, which is equal to, again, same mathematics, Vm over pi minus cosine omega t pi over 0, which is equal to 2 over, similar the one we have, 2 over pi Vm dir VDC. I think we are now happy about this one. We already know the full bridge rectifier, operation of the full bridge rectifier. Now I have a question to you. What kind of values we are going to evaluate the quality of the output? We are going to calculate the RMS value. Bakayım, cevap var galiba. Okay, İsmail bir şey yazmış. Okay, thank you İsmail. Sağ ol. İsmail Başar. İsimlerinizi derste yüz yüze yaptığımdan daha fazla öğreniyorum. Daha çok görüyorum isimlerinizi. Ama yüzleriniz yok. Yani belki şey var aslında e, resimli sınıf tablosu var. Biraz resimli sınıf tablosu üzerinde belki çalışmam lazım. Çünkü koridorda karşılaşıyoruz. When we met in the corridor, for example, you say, hello hocam. I don't know who he was, you know. He is one of my students, but I don't know him. You understand? Or her. Anyway, it's a funny world. I repeat the question. I repeat the question. How do you evaluate whether this output is better or not? The first answer, this is an output. The first answer is this. If this one has AC components, that means it's not very good. We don't like AC components. We prefer pure DC. These are called ripple. The AC components are ripple actually. We don't like it. So we have to reduce it. This is one point. As far as so form factor, ripple factor is defined like this. As far as supply is concerned, we also prefer, we look at the power factor. How much active power we send with the cost of how much apparent power. I come back to power factor equation. That's right. How much input power I send it to this network, however, with the cost of how much apparent power. This is apparent power. I prefer all of my, I don't want to send reactive power to this system. Apparent power, input power, yazacağım denklemlerini. Input power Vs Is cosine phi, output and apparent power and reactive power for AC network, by the way, Vs Is, these are RMS values, by the way, sine phi. For however, VSIS is equal to apparent power. Okay. So power factor actually is active power divided by RMS value. But since input function is not cosine, is not a sinusoidal one, of course, there are some other manipulations necessary. We are going to learn it. But in general, in AC network, pure sine network, input power is equal to VSIS cosine phi, and the output reactive power is VSIS sine phi. So if I come back here, that is the one. We prefer pure DC as far as DC is concerned. Evet, yine aynı denklem bulmuş. Ben hep söylediğim gibi ben şunu tercih ederim. 2 over pi VM. Öyle 0.6366 falan bana saçmalık gibi. Center tap transformer and bridge rectifier, center tap transformed rectifier and bridge rectifier compared, I prefer bridge rectifier since the voltage is divided. You can see that the transformer output voltage is divided by is shared by the diodes, but for that one anyway buna girmeyeyim hiç. Devam ediyorum. Hiç kafanızı karıştırmayayım buralarda. Şimdi devam edelim bakalım ne geliyor karşımıza. Şimdi bakın bu şu network is a R, L and E network. Is electric motor actually. Electric motor model. So rectifier supplied electric motor. Diodes, two diodes and load is RLE. Şimdi size bir sayfa açacağım. Onları yazacağım. Ondan sonra da yorulduk. Bekleyeceğim, bakacağım. Ara vereceğim. Daha sonra veda edeceğiz. Ama önce beni bir dinleyin. Şu denklemi bir yazalım bakalım. Current gene 3 punta mı? 3 punta bile kalın geliyor ya. 2 puntaya döneyim bakayım. 2 punta. Now current is flowing that way. Yazıyorum buraya. Minus Vs t function eşittir delta V diode 1 plus Ri plus L I'm sorry namussuz sabotaj yapıyor. LDI dt plus E therefore bir de arada plus delta V diode 2 var. We generally neglect that diode voltages. Tamam mı? Bunları neglect edelim. Zero kabul edelim. Zero kabul edelim. So the equation here bir dakika ne yapmışım? Yanlış var. Kim bulacak bu yanlışı? Kim bulacak yanlışı? There's an error here. Who is going to find the error? Hadi bakalım. Hadi yoklama yapacağım biraz sonra. Yanlışı bulan alkış istiyor. Hocam Kirchhoff voltage'ı takip edin bakın benimle. If you start with minus Vs, kürsörü takip edin. If you start with minus Vs, the others should be plus plus plus plus. Siliyorum bunu. Yanlışı bulamadınız. Yazıklar olsun. Şimdi bunun çözümünü ben yazıyorum buraya. Bir kere denklem şu. Vs is equal to Ri plus LDI dt plus E. Bunun da çözümü E eşittir steady state solution bir kere E over R. Siliyorum. Minus gelecek önüne. Hadi onu koyayım. Önce sinusoidal voltage source şeyini yazacağım. I is equal to Vm over Z sine omega t minus phi plus transient plus transient minus E over R. That is the solution. Vs tabi burada. Vs Vm sin omega t. Çocuklar önümüzdeki hafta buradan alacağım. Yani bu kadar yorgun saatinizde bundan daha fazla devam etmenin bir anlamı, bir kazancı olmayacak benim için. Sizin için de olmayacak. Şimdi burada bir ara şey yapacağız. Veda edeceğiz burada. Bir yoklama alayım yalnız. Şu anda sınıfta 28 kişi var. Sevindirici. Yusuf, madem ki Yusuf son isim, bu emniyette demektir. İlk isim de hepsini almıyor bazen. Onun için ayrılmayın. Abdülbari ilk isim. Hepsini aldıysa eğer çok iyi. Kopyala. Bakalım aldım hepsini. Evet, aşağıdan 2 tane Y'yi silmiş. Bir de Adil Bayraktar ayrılmış. Bir dakika. Şimdi ben bunu iki Yusuflar ayrılmayın. Sizin ikinizi silmiş. Ayrılmayın Yusuflar. Sizi yazacağım. İlave edeceğim listeye. Yusuf Selim ve Yusuf bir de ayrılan vardı. Adil Bayraktar mıydı? Onun neyse elle eklerim olmaz. Evet, iki Yusuf'u aldım. Ya cep telefonundan dinlediğinizde yazıyor burada biliyor musun? Kopyaladık. Yunus Emre Erdoğan cep telefonundan. Cep telefonundan ne görünür ki burada küçücük şey ya? Abdülbari ilk isim. Evet ayrılabilirsiniz çocuklar. Thank you very much. Bye bye. Tamam. İki Yusuf diyordum ama biri Yusuf, biri Yunus. Kaydettim.
Professor, you can stop recording.
Oh, yes, thank you very much. I'm still trying to write down your names. Okay, thank you. Thank you for reminding me.